At this time I would like to introduce a clearer formula to describe. The number of failures per unit time is equal to the system throughput times the probability of uncorrectable failures. The typical throughput brought into the application is 10 megabytes per second, if the vector of TXRX is roughly 1000 bits with volumes about 80,000 TXRX vectors sent and received per second. What is the difference between 1 times 10 to the power of -4 and 1 times 10 to the power of -7 of an uncorrectable failure rate? The former will have an uncorrectable event between 0.12 seconds, while the latter interval is about 120 seconds, 2 minutes. The viewers of the video can speculate that if we increase the transfer rate to 100 megabytes per second or 1000 megabytes per second, what is the interval between failure? At a speed of 1000 megabytes per second, the system requires a lower error rate than 1 times 10 to the power of -9, because the user does not want a shorter uncorrectable interval, and often encounters failure events, affecting the latency by instability. What is the concept of testing 1 times 10 to the power of -4, 1 times 10 to the power of -7 until 1 times 10 to the power of -9? The error rate of 1 times 10 to the power of -4 is approximately 1 failure in 10,000 attempts. Out of 100,000 attempts, about 10 failed, maybe 7 or 8, maybe 12 or 13. Probably the designer has a foreknowledge that if the result is 1 times 10 to the power of -4, the test volume will probably be 30,000 to 200,000. This test volume depends on the designer's patience. With current computers, these attempts are about a minute or so, and this is a relatively simple cost. What about the estimated result of 1 times 10 to the power of -7? The difference is 1 times 10 cubed times, which is 1000 times. What is the 1 times 10 cubed concept? The cost of 1 minute of testing becomes 1000 minutes, about 16 hours. It is lucky to get the expected result after 16 hours. Please feel difference. Let me elaborate on this difference from 1 times 10 to the power of -4 to 1 times 10 to the power of -7. Oftentimes this is not the case. More of this testing process won't be done just once. If the result is worse, then the time lapse after the debug process has to be done again. It is very possible to change the setting, or it may be done again due to human misfortune. In addition, it may be that the expected result of 1 times 10 to the power of -7 is 1 times 10 to the power of -6, and the candidate needs to change the parity matrix again, then it is necessary to try dozens and hundreds of matrix candidates one by one after testing and selecting. If a potentially suitable candidate is selected and the sensitivity to decoding is further tested with other settings, large error rate fluctuations due to reliance on unreasonable soft decoding may be uncovered. I was so sorry to say, discard this and move forward to test the next. After going through a full process, for a multi-length ECC family, you need to examine every ECC mode. Maybe parallel processing can speed up testing, but 20 or more sets of long-term simulations at the same time is tedious and tiring work. The ECC coding quality depends on the patience of the designer. Most players did it by lowering the verification criteria. When someone wants to improve quality verification, they are faced with the current market situation where bad money drives out good. Let's go back to 5G. Why does 5G fail in ECC parts? Let's take a look at the chairman's summary. One question is the number in the y-axis to 1 times 10 to the power of -3. There are similar figures about LDPC in the form of BG1 and BG2 and polar code. Was it ready for a high-speed future? Yeah. This was for the 5G system in 2016 to 2017 discussions. Nothing improved after that. Push stop button if you need to see it clearly. The second question is its flexibility, how to meet different lengths among all modes. Its idea uses lift size to change the size of the matrix. Such problems can make digital design complex. Design multiple similar barrel shifters and mucks to make placement and routing complicated. My suggestion is to use a fixed one, such as the QC_size variable I define to the power of 2, such as simply 64 or 128, and then design different lengths as multiples of QC_size without changing QC_size. The design process is using fixed size floor tiles at the floor plan stage. The third question is length design. My proposal is that the system should design the length in binary notation. Using binary representation to change the complexity of O, log, the easiest way to reduce the design. Finally, through my work promotion at Final Page, you can know what is the best ECC design at this stage.